Welcome back to Chapter 2, Lines and Planes in R3. In this video, we are going to do Section 2.2.2, the vector form equation of the plane. So let's just go and review. I've cut and pasted the top of the chapter here, planes in R3. Our goal was to describe in 3D space a plane using a general equation and a vector equation. The general equation we saw in previous videos was ax plus by plus cz plus d equals 0, and that relied upon the normal vector of the plane. In this video, we are going to do the vector equation of the plane, and we are going to be using instead these two vectors d1 and d2 within the plane. So let's go ahead and do that. So the vector form equation of the plane, here we're said let pi be a plane in R3, and we are given a point P, x0, y0, z0 in pi, and two non-parallel vectors, d1, d2 in pi. And we are asked to derive the vector form equation for the plane. So we're going to start out actually the same way that we did in the previous derivation. We're going to let q, x, y, z be any point in the plane. And so let me go and draw it here. Let's put q over here. Now in the previous derivation with the normal vector and the general form, we relied on vector pq in the plane being perpendicular to a normal vector. We're going to do something different here. We have two vectors that are in the plane now, or parallel to the plane, not perpendicular to it. And so what it turns out that we are going to rely on is our good old tip-to-tail relationship. We can scale these vectors d1 and d2 so that we can form a tip-to-tail relationship with our vector pq. So for example, this vector down along here, that's a multiple, that's a scaled version of d1. So it's s times d1 for some s, for some multiple s, and then we have here some multiple of d2, right? This is t times d2. And using our tip-to-tail relationship, then we can see that our vector pq in the plane can be expressed as some multiple of d1 plus some multiple of d2, where s and t are the appropriate multiples given where q ends up by being placed. Now, remember, this is just a sketch, but we do have an origin somewhere, so let me just add it here, reminding ourselves that p and q have positions and can be expressed here as, right, pq is oq minus op, and that obviously is still s times d1 plus t times d2, and then solving for the unknown, right, q is any point, p is given, so op plus s times d1 t times d2, and then filling in the components that we know. So any x, y, z in the plane can be expressed in terms of the known point and two vectors parallel or in the plane. So d1, 2, d1, 1, d1, 2, d1, 3, and vector d2. So now we start getting messy with the subscripts d2, 1, d2, 2, and d2, 3. There you go. So this is the vector form equation of a plane, given that we know a point, x0, y0, z0, and two vectors in the plane. So I want us to remark upon the similarity to our line equation, right? We have the x, y, z We have a known point. We have a direction. Here instead we have not just one, we have two directions. And we'll remember for a line, right, for a line we had a start point P, and we could use multiples of the direction vector to get anywhere along that line. We only needed one vector because we were going in sort of either one direction or the other, one-dimensional. If you add a second vector to that, if you add a second vector possibility and you scale those two vectors, well, you can reach sort of everything in between, which is exactly what is happening here in the plane. Secondly, I want to point out the difference, right? The normal form equation that we used before, ax plus by plus cz plus d equals 0, it relied on the fact that we had a vector perpendicular, and our vector pq here was perpendicular to the normal vector, right? We had that relationship. PQ was perpendicular to the normal vector. We are doing something very different here. We are staying within the plane for the vector form equation. We are scaling vectors in the plane to make a vector addition, to make a tip-to-tail relationship. A different characteristic of vectors gives us a different form equation for the same plane object in R3.